Dennis Ganano with US Bridge. I take care of engineering and sales in Ohio here for our company. And I want to thank you, Michael, and I want to thank everybody who's tuned in today. We really appreciate your interest. Our discussion today is going to go over general concepts of truss bridges. We'll focus on a set of Ohio projects that have something to teach us. That'll lead us into some cost data that I'd like to report on, and then we'll review everything we've talked about and draw some conclusions. So jumping right into it, I want to show what generally are the most suitable conditions for truss bridges. We see site conditions that have lower traffic volumes for city streets and rural roads. That's going to be a condition that we look for. Facilities with 3 lanes or less, nearby driveways and intersections also are something that are cause for interest for truss bridges. We're generally looking for short span steel bridges. They're going to be between 75 and 275 feet in span length. When piers are prohibitive or undesirable, that might be a cause for considering an alternate that's a steel truss bridge. When superstructure greatly impacts the project footprint, when the depth of the superstructure is getting deeper and deeper and causing impacts to your project footprint, steel truss bridges might be a very good alternative to look at. And lastly, when visibility of that bridge or aesthetics are important, those are all good reasons to consider a steel truss bridge. And that brings us to, what are the things that bridge engineers need to consider? They're considering that structure depth is going to affect the beam depth, or the site is going to be cause for looking at the structure depth. Whenever you're replacing a bridge, many times you're stepping back behind the existing abutments, your span's growing a little bit. Depth becomes important. You have to consider if there's piers going to be constructed in the water, they're going to take up some of your conveyance opening. Your beams are getting longer, so then therefore things are getting deeper, which has an effect. These are all the classic parameters that bridge engineers need to consider when they're siting in a bridge. And of course, structure depth drives all of those things. So how does a truss bridge, a short span steel truss bridge, help with that? What is it that drives that to be a good solution? Well, the truss girders of the bridge are set outside of the roadway, and they can be as tall as needed and don't affect that lower low steel elevation. The floor beams span the short direction. They're going to be below deck, and they're going to only be spanning the roadway width. And so what ends up controlling structure depth, of course, is the transverse floor beams. So in this diagram, you can kind of see that there's a slab beam bridge on the left and a truss girder bridge on the right. And relatively speaking, we've got a structure depth advantage. Here's a good view of long span steel truss bridge in upstate New York, creating a nice and large hydraulic opening where you can see the truss girders are outboard of the roadway, very deep. Transverse beams are going to be below that deck, framing into those truss girders, keeping things very, very shallow. So naturally, when we start to discuss these things, people want to know what are our max spans. What do we recommend for our max spans? We got a pony truss on the left and a through truss on the right. So we like to recommend these lane and span limits. These are good rules of thumb for us to be able to design and fabricate. So as I mentioned, I'm going to talk about a special set of bridges projects in Ohio. They can teach us a lot, and the reason that is because this group of bridges are federally funded. They have good transparency into the total project costs of the bridge projects. They've been programmed through ODOT and administered by our County Engineers Association in Ohio, which means they select the projects, they prioritize the projects, they administer those federal funds coming through ODOT and to their association and out to their county engineers. These projects have followed ODOT's construction specifications and their pay item catalog, and they have followed an environmental documentation process. Their plans have been developed by the counties themselves or by consulting engineers, and the site plans that I'm describing are really the bid set that hits the street for bid. But these particular projects follow sort of a unique construction letting process. It's a design bid, design build process. So the site plans have everything they need to construct foundations, the abutments, the roadway improvements, cross sections, profile grade, all the pay items for roadways, for foundations, for abutments, but the superstructure details are not fully developed until the construction project's been awarded, and then a contractor taps a design build fabricator to design those plans to augment the original plans during the construction phase. We do that all the time. Here's a list of those federally funded jobs in Ohio. There's 31 of them since 2008. We've got several going currently this year and planned for next year. But what we are going to look at is 18 projects that have dissected and developed cost data for. And since we don't have enough time to look at all 18 today, I picked 6 to really kind of do a little bit deeper dive. Here's the first set of 6 of the 18, the little gallery. I wanted to show a lot of, at first they look very similar, but really there's a lot of distinguishing differences in each job. I'll point out just a few things in this gallery until we dive deeper. Slide or a photo in the middle, lower middle, is Jackson County Roberts Road, and it featured the first monochord, twin monochord design that we had done. It's a monochord you'll see a better picture of later, but it's an integrated gusset and bottom chord plate that's spliced between panels. Just beside it is Muskingum County's Lambert Road, and what you can see there and learn is that skewed framing and skewed bridge arrangements and alignments are not a problem with steel truss bridges. This slide also sort of shows the variety of spans and widths here. We have everything from a 90-foot by 20-foot bridge to a 150-foot span by 28-foot roadway. On this set of 6, we just mentioned that the bridge in the upper right, Calendar Road, that's our longest span, longest pony truss in Ohio. It's 170 foot by 28 foot with 2 50-foot approach spans. It's a highlight to take note of. And then on this page, I just want to mention on the left, upper left, Perry County's Flagdale Road had a vertical curve built within its framing and its concrete deck construction. And it's again, vertical geometry within a steel truss project is not a problem at all. Similarly, the lower center bridge, Bennington Chapel Road features a jointless end of the deck construction as it transitions to the approach slabs. We used a deck extension that extended up past the end stringers over a stubby little back wall and cantilevered behind it and married up to the approach slab, which pushes the cold joint beyond the back wall. And on the far right, at the bottom, is Muskingum County's Hamby Hill Road. The unique feature there that is worth mentioning is we had staggered continuous stringers over multiple spans, 2 or 3 spans across their floor beams to match criteria with the panel spacing, which was under 14 feet, which allowed us to decategorize those floor beams from being fracture critical, which is an important feature to mention. So with that, and before I jump into the deeper dive on the 6, I want to point out, make sure that everyone is looking for the difference in construction that you'll see. Some of the bridges have floor construction, some of them have slab construction, and the floor construction is made with elements that sit flat, and they're laid flat onto the steel stringers, bolted or clipped to the framing members below. And then, of course, when we're building slab construction, we are going to crown the soffit of the bottom of the slab with forms and haunches. And it's going to be a structural deck that's built, and the form work is not structural. It's light gauge, just enough to hold the wet weight of concrete and construction crews. Contrasted again back to the floor construction, and the floor is structural. It's heavy gauge corrugated steel floor, or you'll see in a minute some laminated timber panels that are structural. Those are options for floor construction and slab construction. So here we dive a little deeper into Richland County's Stouffer Road, 132 foot by 28 foot galvanized steel truss bridge. It has a depth of 3.125, structure depth of 3.125 feet. It uses a lot of ODOT standard details, such as the twin steel tube railing, expansion joint details for strip steel. It cost $1,029,000 in 2017 overall for the project cost. Here's a view of the roadway. It's a 28 foot wide roadway from rail to rail. And here's sort of the troll's view of the bridge from underneath. We've got what you can see is the formed bottom of the deck slab. Form has been removed. You see the bottom of the deck slab with its haunches. This was composite construction, had shear studs on the floor beams, and it had twin plate bottom chords. Here's a view of the expansion joint, just doing its job, filling up with grits, but it needs to be cleaned out, but it's not leaking through, and it's providing a good dry condition on the abutment seats. Now we take a look at Miami County Croft Mill Road, built in 2020. It also is a deck slab built on stay-in-place formwork, again using some ODOT details like strip seal for the expansion joint and twin steel tube railing along the roadway. Its depth was 3.96 feet. It was $1,109,000 back in 2020. And here's a roadway view. You can see the textured slab on top. The nice setting. This bridge had a very very nice location. It fit in very well, and it replaced an old truss bridge that people were used to, but it lengthened it and widened it. Turned out to be a nice project. Here's a view from underneath. You can see those stay-in-place forms between the stringers. They sit on light gauge bent plate angles that are attached to the stringers. We do two different ways of attachment. Sometimes they're welded directly to the stringers, and sometimes they're supported with bracket members across those stringers. Here's a close-up view of the bottom cord plates, twin plates on the left, and then the embedment anchorage into the slab, turn down portion of the slab supporting the railing posts. Here we see Johnson Road in Ashtabula County, Ohio, over the Grand River, which was a scenic river in the state. It provides for a 3.5 foot structure depth. It's a 162 foot span over the river here. And its floor construction was made from glulam timber panels, bolted through with dome head bolts, and then waterproofed and asphalt paved over top. There's a view from the side view or elevation view of the bridge. These are framed floor beams and framed stringers into those floor beams. Here you can see some of that and the timber panels from below. Here's the end of the bridge, the abutment view. You can see the truss bearing, shoe and pad, and then also an end floor beam, which picks up the last panel of stringers. The access panels are to provide for, or the access holes that you see there provide for an erector to get tools behind there to finish tightening the stringer clips. There's no step up for separate stringers. It's just one constant seat across there. Here we have a much shorter bridge, an 80 foot by 24 foot bridge in Marion County on Township Road. It replaced an old historic bridge, truss bridge at this site. It was made a little bit longer and I think a decent amount wider. It uses the 5-gauge steel corrugated floor. It has concrete poured in those corrugations to make a flush, flat surface, and then it's waterproofed and paved over as well. It was a design build project that was worked on by two sets of consultants, one to put the package out as a design build proposal, and then once it was awarded, contractor had to hire another engineer to develop the full details of the whole project. And we were part of that team to provide the steel details and steel design of the bridge. Here's before paving. You can see the type 3 waterproofing was put down. It was packed down, then laid out and over top of a stainless steel drip strip on the sides. And then this would be paved once it dries out. Here's a view of the abutment and its bearing and the abutment seat and step for the abutment seat beyond. You can see the asphalt paving and the drip strip on the right or up above the bottom cord there. And in this oblique view, you can get a very good view of that twin steel plate monocord that has the integrated gusset plates shaped within the plate that creates the bottom cord. This bridge has a fairly low crossing, so you can see that was a consideration why the truss bridge replaced another truss bridge. Here we have Muskingum County's Okie Road, 100-foot by 22-foot bridge on a township road. It provided a 2.625 foot deep structured depth. It was a concrete slab on stay-in-place formwork. So built 2 years ago and had a very, very shallow structure depth. Here you can see again a monocord, twin monocords on the for the bottom cords. Came in 3 field sections, and you can tell that by the splices in the bottom cord. Here's a view from below again. We have only 4 stringer lines, so you can tell the stringers are a little deeper than things that we've seen in the past, just recently looked at. Here's a view of our crews setting floor beams as after the 2 truss girders have been set, they've been stabilized and guide down to the ground. To dead men, we've then get floor beams erected across there. It becomes fully stable, and then we frame it out with the rest of the stringers and floor or formwork. Here we've got 116-foot by 28-foot steel truss bridge in Wyandotte County on County Route 16. This utilizes corrugated steel floor, and we fill the corrugated steel floor with a deeper fill reinforced with a single layer of reinforcing for temperature and shrinkage. And it's hard topped as a durable roadway surface. You can see here that the steel floor is laid flat and clipped to the stringers. And again, the floor is contained with edge dams. The concrete's contained with edge dams and screeded off with a power screed. Here is a close-up of the laminated elastomeric bearing pad and the stringer seats beyond. And this is a pretty common scene when we're erecting a truss bridge in Ohio. We're going to set up usually on the roadway many times if we can. We're going to use farmers' fields or undeveloped quadrant of the site to bring in our field sections. We're going to splice those together into one full truss girder. Pick that up. This particular crane was a 450-ton Liebherr crane. And once those trusses are set, we set the first one, like I said, guy it off, stabilize it, bring in the second one. While we're holding on that, we may be able to put floor beams in, or we may guy it off too, and then use the same crane for erecting the floor beams. So with that, here's sort of a cost data summary of what I pulled together. I used this to develop fabrication averages, installation averages, and the remainder of the project, all other. And this is sort of the crux of the presentation, to share with engineers and bridge engineers and folks that develop projects. This is for your use in terms of programming and estimating costs for future projects. Those projects may max or min out depending on a lot of times, the construction of the abutments, the depth of the foundations, complexities of those things. All other is a category that includes everything but the fabricated and delivered bridge and its installation. So in review, truss girder position allows for that very, very shallow structure depth, helps limit the profile rise needed, and minimizes the project footprint. It helps lessen environmental impacts, helps simplify permitting reviews. It's very competitive when you consider all costs considered together, especially with the idea of multiple spans and pier constructions or deeper and deeper members, which create more and more embankment construction and project limits. We've also gone over, these are all very highly customized scopes and specifications specific to the project and the needs of the project. There's very little standards to go by in terms of the truss bridge itself. So they are very customized. And we use sort of a design bid, design build process to get there, collaborating before and after award of the contract. So if you're considering developing a project and you need to evaluate alternatives and your site constraints warrant it, we've gone over those. You're in need of some preliminary details, cost estimating, or reactions for your abutments. We work with engineers to get those. And that's why I wrote, if only there was a library of design plans and bid specs, plan notes, installation drawings, erection procedures, photos, if only. Well, there is. In compiling all this information, I'm able to provide and share with project developers and engineers these kinds of things, this kind of information. So there is a place to go and get that kind of information. We collaborate with designers all the time doing that. So I do want to mention that's how you get a hold of us at info@usbridge.com. And I'll leave it at that.